Hi, welcome back. Today we're going to learn about geometric sequences. This is lesson 10.3. In lesson 7.1 we learned about arithmetic sequences right after learning linear functions. And today we are going to be learning about geometric sequences right after learning about exponential functions, right? So there is a reason to that. So let's take a look at why we did it the way we did it, all right? So the arithmetic sequence, let's recap. The pattern we saw in an arithmetic sequence is a linear pattern. All right. So if I have an example of an arithmetic sequence, say 2, 4, 6, 8, 10, I'm seeing that there is a constant change in my y values. The term values are actually my output, my y values. So I'm looking at my two consecutive terms. I'm seeing there is a common difference between the two consecutive terms, which is adding a 2 every time. All right. So if I were to graph my arithmetic sequence, I will get a linear pattern in my graph. So that's why we learned arithmetic sequence right after learning linear functions. So as we saw, we see that two consecutive terms have a common difference. It's represented by the letter D. And we also talked about representing a sequence as a function. We needed an input, which is my term position or the term number, and we needed an output, which is my term values, or my actual terms in the sequence. So since it's a function, I can write a rule for my function. One rule we wrote was the explicit rule, in which we related the output, which is the term value, to the input, which is the term number or the term position. And the second rule we wrote was the recursive rule, in which we related the current term to a previous term. Current term value to the previous term value, provided you are given your first term. You need to know where you start from, and once you know what you start from, you do something repeatedly. That's why it's called a recursive rule. So you're doing something repeatedly to get your terms in the sequence. So you're relating your term value, your current term value, to a previous term value. All right. So today we are going to look at our geometric sequence. In this geometric sequence, we need to first observe what pattern the geometric sequence has. So in a geometric sequence, let's first use an example to understand our geometric sequence and understand the pattern in our geometric sequence. So here I have an input, which is my term position, and I have the output, which is the actual sequence itself. So this is my actual sequence, 2, 6, 18, 54, and so on and so forth. And this is my term position. This is my first term, second term, third term, and fourth term, and this is my nth term. So in my geometric sequence, first we need to identify what the pattern is. So if I look at the sequence itself, which is 2, 6, 18, 54, and so on, I'm looking at it, does it have a common difference? 2 plus 4 is 6, 6 plus 4 is not 18. So this is not an arithmetic sequence. So let's identify what other pattern does it have. So if I look at this sequence much closer, I'm seeing that from 2 to 6, the two consecutive terms got to multiply by a 3. From 6 to 18, again I have to multiply by a 3. From 18 to 54, I multiply by a 3. So I'm seeing that pattern here. So which is a pattern of an exponential function, right? In exponential function, we saw this and we called it something. We called it as our, yes, that's your common ratio. All right. So in my geometric sequence, the two consecutive terms, they have a common ratio. In this case, the common ratio is represented by the letter R. It's represented by the letter R. So the pattern is an exponential pattern. That's why we are learning geometric sequence right after we learned about exponential functions. All right. So we know that sequences can be represented as functions. So we are going to learn about writing rules for our function. The first rule that we are going to learn is our explicit rule, which relates your output to your input directly. So this is my output f of n, the term value, each term value, and this is my term position or the term number. So let's go ahead and rewrite our sequence in a table form. So I wrote this again. So I have my sequence. My first term is 2, second term is 6, third term is 18, fourth term is 54. So I want to get to a general rule to generate my sequence. Alright. So I have my f of 1, which is 2. My f of 2, how did I get my f of 2? The common ratio is multiply by a 3. The common ratio is multiply by a 3, right? Common ratio is multiply by a 3. So to go from f of 1 to f of 2, I have to multiply it by a 3. So I take my first term and I multiply it by a 3. To go from f of 2 to f of 3 or f of 1 to f of 3, say, if I want to go from f of 1 to f of 3, I have to multiply it 2 times. So I take my first term and I multiply it 2 times. Alright. If I go from f of 1 to f of 4, I would have multiplied it by 3 times. So f of 4, so I take my first term and I multiply it by the common ratio 3 times. I can keep on repeating this pattern. For f of 5, I would have multiplied it by another 3. I would have gotten 150, 162. Right? So I take my first term, I would have multiplied it by a 3 one more time. Right? So as you can see, repeated multiplication is exponential. Right? So I can rewrite this as, I'm not multiplying the first term by any 3, but just to have the pattern there, I'm going to put it as 3 to the power of 0, which will make it to a 1, and I'll still have the 2. So this is, take my first term and I multiply it by 3 to the power of 1. I take my first term and I multiply it by 3 to the power of 2. 3 times 3 is 3 to the power of 2. I take my first term and I multiply it by 3 to the power of 3. I take my first term and I multiply it by 3 to the power of 4. So if I have to generalize this pattern, so I get my 2, I'll get my 6, I'll get my 18, I'll get my 54, and I'll get my 162. So I got my sequence that I started with. Alright. So if I have to generalize this pattern, so what will it be for f of n? F of n, I would have taken the first term and I would have multiplied by a common ratio. What will be my exponent at that point? Alright. So if I look at the pattern, if it's the fifth term, my exponent is 4. If it is the fourth term, my exponent is 3. For my third term, my exponent is 2. For the second term, my exponent is 1. And for my first term, the exponent is 0. Alright. So every time my exponent is 1 less than my input. Alright. So this is n minus 1. So that will be my exponent. So this is a specific rule for this specific sequence, this specific geometric sequence. Okay, so if I have to write a general rule for an explicit rule, so general explicit rule for any geometric sequence, general explicit rule for any geometric sequence, f of n, my 2 is my first term, which is f of 1, and I multiply it by the common ratio, which is represented by the letter r. Common ratio represented by the letter r. How many times do I multiply it? To the power of n minus 1. So let me rewrite it because I made a boo-boo there. F of 1 times your common ratio to the power of n minus 1, because repeated multiplication is exponential. So this is my explicit rule for any geometric sequence. So now let's take a look at how to write a recursive rule. Alright, how to write a recursive rule. We saw that recursive rule relates your current term to a previous term, right? It relates your current term to the previous term. So let's rewrite our sequence. My first term was 2, my second term was 6, my third term was 18, fourth term was 54, fifth term we figured it out, 162. It will go on and on up to f of n, right? So this is my sequence. So now how do I write my recursive rule? In my recursive rule, I am relating my current term to my previous term. Also, I am giving what f of 1 is. Alright, so always recursive rule, two-part rule. I need to know what my first term is, where I am starting. Okay, so this is a common ratio of 3. Common ratio of 3. Alright, so when I look at it, f of 1 should be given, so I have to give that. F of 1 is 2. F of 2 is I take my first term, which is 2, and I multiply it by a common ratio. So this is f of 1 times 3, right? For my third term, I take my second term, which is 6, and I multiply it by a 3. This is f of 2 times 3. For my fourth term, I take my third term, which is 18. This will give you 18, right? This will give you 2. This will give you 6. And this is 2. All right. For my fourth term, I take my 18 and I multiply it by a 3. So that's f of 3 times 3, which will give you 54. For f of 5, I take my fourth term and I multiply it by a 3. So that is f of 4 times 3, which will give me 162. So if I have to generalize this rule, my f of n will be whatever the previous term was, which was f of n minus 1, and I multiply it by the common ratio, which is 3. So this is applicable, as you can see, only for n greater than or equal to 2, because first term I'm giving it, right? So how do I write the general? This is a rule that is specific for this particular geometric sequence. But how do I do it for any geometric sequence? So general recursive rule. General recursive rule. Remember, it's a two-part rule. I have to do what f of 1 is. I have to give what f of 1 is. F of 1 is given. And I have to write a rule for f of n. I take my previous term, and what do I do with the previous term? I multiply it by the 3, which is the common ratio, right? So I multiply it by the common ratio. So that will give me my terms in the sequence. This is for n greater than or equal to 2. So this is a general recursive rule for any geometric sequence. Alright, so please practice this. Look at all the other examples. We will go over them in class if you have any doubt. So most are self-explanatory. So if you have any difficulty, please make a note of it in your notes, and then we will go over it in class. Alright, thank you.